Alright, we ended the last video with this question. How can we algebraically determine the x-coordinates from the quadratic function given here? And remember, when the question says algebraically, they're looking for a written method. Okay, so investigate how to obtain the x-intercepts in standard form. So first, we'll use the aid of a graph, and then we'll move away from the graphs into how we do it without being shown a graph at all. So we'll go to the website I've mentioned before in this chapter, Desmos, and we'll graph each of the following quadratics. There are 4 we're going to graph. We have to state the coordinates of the vertex, the axis of symmetry, coordinates of the y-intercept, and coordinates of the x-intercept. Keep in mind we complete the coordinates of the y-intercept without even having the graph. So if we just look here, at least that was the last value. So coordinates of the y-intercept, if I'm going to list them as x-y pairs, it will be at 0, 12. So I know it should happen here. If I go to this graph, well, now I can't see it so easily. And what I would have to do is insert a 0 for each x. You have to remember that, or you should remember, that at the y-intercept, where you cut through this y-axis, the x value is 0. So if you put a 0 in here, and a 0 in for the other x, you have 0 minus 2, or negative 2, 0 subtract 6, negative 6, and it will still be a 12. And to graph both of these, we'll move down to our next 2 questions after. Graph's been entered into the website. Now each of the points that we were interested in, y-intercept here is 0, 2. First x-intercept is 2, 0. Second x-intercept is 6, 0. Vertex is 4, negative 4. And we know that the axis symmetry will run straight down through the middle, so it should be x equals 4. All right, going back here, enter in each of those values. And I'll just trace the shape of the curve. So an arrowhead there and an arrowhead here, just show the graph continues. We'll do the same for this one. All right, now I've entered the equation here in a different form, and we'll learn this is called factored form. And it turns out to be the same equation. So 0, 12, x-intercept is 2, 0, 6, 0, and the vertex is not changed. You should note a connection between these values here, 2 and 6, and 2 and 6 there. Well, here, negative 2, negative 6. So I won't graph this one. I'm just going to say they are the same. So 2 more equations that need to be graphed. This function here and the next one below. Okay, the third graph is placed there. The x-intercept is negative 1 and 0. Second x-intercept is 3 and 0. The y-intercept is 0, negative 6. And the vertex is 1, negative 8. And the axis of symmetry will be x equals 1. Okay, we've plotted each of the points here and done a sketch of our graph. For this equation, we're asked to do the same. If you were to graph this one, you'd find that each of the values would be the same. So these are 2 versions of the same equation. And from this one, you should start to notice a pattern between these values here and the coordinates of your x-intercepts. And here and there. Okay, now using the results of quadratic functions and their respective graphs answer each of the following questions. Which form of quadratic function is easiest for determining the x-intercepts with that graphing? And the two forms we went over are standard form, and here we have the factored form. And the value of a is the same in both of them. The one that would be the easiest for determining the x-intercepts are here. And how can we obtain the x-intercepts by looking at the quadratic function? It's the opposite of the values that you see here. So if you look back up to the past equation, the opposite of 1 is -1, and that's one of our x-intercepts. And the opposite of -3 is 3. And that works so long as we have the a value factored outside. So then this question, what's the connection between the factored form quadratic function and the x-intercepts? Well, here you have x subtract 2, and our x-intercept would end up being 2, or think of it as 2 and 0, and the other x-intercept would be x subtract 6, and x equals 6, or 6 and 0. Okay, the last question, what's the value of the y coordinate at the point where the graph crosses the x-axis? Well, the value of y on the x-axis, think of it like this. It could be 10, could be 5, down here on the y-axis, the value, or on the x-axis, the value is 0. So the zeros of quadratic function represent the position where the height is 0. So you're looking at where the graph is touching the x-axis. The zeros of a quadratic function are also referred to, they're known as roots. Or x intercepts. So this question here, the example, how can we determine the x-intercepts of the quadratic function shown? Well, we know that the y value is 0 when you're calculating the x-intercepts. So we want to find the value of x when the y value is 0. So find the value of x when the height is 0. So the factor, so our two factors of 12 to add to give us -8. So factors of 12, 1 and 12 can't be added or subtracted to get an 8. 2 and 6, they can be added to get an 8. So you have x minus 2, x minus 6. Sorry, there should be a 6 there. So multiply them, we get positive 12, add them, we get -8. And what we're going to make use of is what I've mentioned in class earlier. That's called the zero product property. If you're going to multiply two numbers together and the answer be 0, then one of the numbers has to be 0. You can't multiply two numbers because 0 is an answer, but one of them being 0. So either this here bracket is going to be 0, or that bracket there is going to be 0. And we don't know which one. Sometimes both of them will work out to be. So write x subtract 2 equals 0, or x subtract 6 equals 0. Bring the 2 over to the other side. You want to solve it for x equals. So the x-intercepts are 2 and 0, and 6 and 0.